No, let's start class. Okay, so I'm recording. I'm going to change the camera so I don't scare anybody to death. All right, what do you guys want? There's a test tomorrow. What can I do for you? A little louder, please.
The last assignment,
Yep.
I was just confused about the energy being measured in kilowatt hours. Like, I thought joules was what energy was supposed to be measured in. So I was just a little confused with that one.
Is it the question number 5?
Number 4, like 4A was where I was confused. I understood 5.
Okay. How much solar energy will the solar panels transform into electrical energy each day? And so are you saying that the answer was given in kilowatt hours?
Yeah, like I understand. I just need to like have an explanation of the difference between a joule and the kilowatt hours and why they would measure in them differently.
Okay, give me one sec. Let me see, because I know I had, where's my, let me just look, because I know I had it before I find it in the notes. I know there was, I kind of touched on it with the notes, so let me just see as a starting point. Just gonna wait for Keynote to open. Okay. No, it's not even an explanation. All right. Okay, so I guess what I'll do is I'll just kind of do it and then kind of explain my way through, and as I go, if something doesn't make sense, then just scream. All right, so number 4, families of 5 is planning to install solar panels, a family of 5. See how they throw in extra information? Right away, I want to write down 5. That has nothing to do with anything. Who cares how many people are there? Well, actually, maybe I need to finish reading the question, but I have a feeling it doesn't matter. Plan to install solar panels on the roof of their home to help reduce the cost of electricity and save energy to help the environment. The family plans to install 10 panels. Okay, so there's 10 panels, each with a power rating of 600 watts or 0.6 kilowatts. On average, a solar panel can produce electricity for 4.5 hours per day. I'm gonna make this 0.6 to go kilowatts. How much energy will solar energy will the solar panels transform into electrical energy each day? Okay. So each day. So with this number here, 10 times 0.6 times 4.5 is 27. And is that what you got for the answer?
Yeah.
Okay. So now, so what I did here, this is in hours and this is in kilowatts. If we changed this to seconds, then this could be joules.
So what is a joule though? Because I thought that was like a Newton per meter, but if it's electricity, it's not displacing anything.
Yeah, see, and that's why, like, work equals energy. So work can be force times displacement. Energy can be 1/2 mv squared. It can also be mgh. It can also be 1/2 k x squared. This is elastic potential energy. K is a constant. X is the distance that it's stretched or compressed. So it's just one of those things that kind of can cross over. It's known by one thing, but can be known by another. I don't know how else to kind of mention that. Like, I know, did you read the chapter at all?
Not all of it. I did read a little bit.
There's a
yeah, like it explained that it's because energy equals power times time.
Yeah.
So then you put watts and then the time, and that's energy.
Yeah. Yeah, it's I'm not sure how else, in all honesty. I will tell you, if it's not talking about like a charge cents per whatever kind of on the test, you don't have to worry about this. You have to worry about this when we're talking about what it's going to cost. So it's not like I'll ever ask, so and so jumps from a diving board. what is his energy in kilowatt hours? Like that'll never happen.
So this is when we're talking about like solar energy or anything like light bulbs or like the cost of running them or something like that.
Yep, exactly. The cost of running them. Yep. Like I'll tell you, I'm just looking for it on the test because I have it in front of me. Yeah, the only question that has anything to do with kilowatt hours has a cost associated. Does that kind of help, Nathan? I feel like it's not getting right to the root of things. Okay, well, that's good. Ada, are you kind of okay with that? Mostly-ish?
I think so. I think I tried this question like twice because I didn't know how to kind of like, you kind of had to like convert stuff to like plug it in.
Yeah.
So I like, I don't know. I divided it by,
Time.
I don't even know what I did here.
You might have
But
divided because that's the temptation.
I times both sides by 10 because there were 10 solar panels. So the 4.5 I also multiplied by 10.
Oh, yeah. You only need to do that once.
I don't know what I did here, but I got the right answer. I don't know.
Good. I don't know either. Other questions?
Yes.
What are they?
On page 229.
Recording this? Yes. 229. Okay.
I'm just gonna get there. 229. Oh yeah. Okay. So 7B.
Okay.
I'm just trying to figure out what I wanted to ask here.
Didn't we do this one in class?
I don't know. Maybe I wasn't there.
We did do this in class.
I've skipped like 2 days for appointments recently.
Yeah, but that was much more recent, wasn't it?
Yeah, like me skipping. Yes.
Yeah. Well, I guess
Maybe.
What's that?
You want me to look back in videos?
Yeah.
Then?
Yeah. Maybe have a look.
Okay.
Look back in your notes, and if you're still stuck, then for sure I'll help you. But yeah, if it's out there, then
I think too when we were talking about mechanical work done in like the vertical, and we're using the acceleration like vertically.
Yeah.
I don't understand when it's asking for the mechanical work why we don't subtract the 2.2 from the 9.8, because one is accelerating up and one is accelerating down.
You would subtract. Okay, this is a good question. You would subtract the 2.2 from the 9.8 if it was going in the same direction.
Wait, can you say that again?
You would subtract the 2.2 from the 9.8 if it was going in the same direction. If you're in an elevator on a scale and you look exactly like this, and if the elevator is going at a constant velocity, so there's zero acceleration, let's say you weigh 100 kilograms, then it'll be 980 newtons. Okay, just saying 100 kilograms just because it's easy to multiply. So 980 newtons, this is when acceleration equals 0. But when acceleration, what have I got myself into? I don't want to keep drawing. If acceleration in this case equals 2, let's say just 2.2, and it's going down, then this scale will be lighter. It's going to be 100 times 7.6. So this scale will say 760 newtons because you're going down. So gravity kind of isn't working as hard because you are already kind of going in that direction. It's kind of like, hopefully this doesn't confuse things, but when I talk about FS max, like maximum static friction, there is a maximum, but like, so when I push here, let's do visuals. If I push this this thing here, I'm pushing this around, and it resists a little bit, but it's not resisting very hard. But if I push very little, it's not moving. It doesn't mean all of the static friction is being used, but just enough. But if I push and push and push and push, and then it moves right before it moves, that tells me kind of what the maximum is. So it's not using all of its power to hold still, unless it has to. Same as me like pushing on a wall. If I push on a wall and I push with 5 newtons, and it doesn't go anywhere, we don't say, oh, that's all that the wall can do is 5 newtons. No, it just meets me as much as it needs to.
So that positive acceleration just acts a bit against the negative acceleration, so it has a less of a negative acceleration.
Well, technically it acts with it.
So
Like,
why would you
It's
subtract?
like if you're swimming in a river that's flowing, if you're going with the river, you're going to go faster than you would normally.
Oh
if you-
wait, it's accelerating down, you said.
Yeah,
But if it's accelerating up is what I was thinking, then you would subtract it.
Yeah. that's what I was going to get to. No, then you add it because you subtract it here. Notice it's less. If you're going up, so this arrow is associated with this and this one here. If you're going up, then it's 9.8 plus 2.2, so it'll be 12. So it'll be 1200 is what the scale will read. If the acceleration is 2.2 up, because if the elevator is accelerating up, it is going against gravity. It's this kind of tug of war. So you will feel heavier on the scale. You'll feel lighter when it goes down.
So if you're just standing still, then you would be accelerating at 9.8 meters per second, technically.
Yeah, yeah. It doesn't feel like but your muscles are resisting it. You know, if you just like relaxed all your muscles, you just drop because now you're not fighting acceleration. You're not fighting gravitational pull. Like you reach for a drink of water, you think, well, I'm not fighting anything. You are constantly. If you go to pick up a weight, you have something somewhat heavy in your house. If you pick it up slowly, it's kind of more under control. You won't really notice the weight, but if you're trying to do it fast, and this is tricky when I talk about weights because there's all kinds of different things that happens when you go slow versus fast, but you pick up something fast, it'll feel heavier. If you swing something around your head, something light, and you're swinging it around your head, the faster you go, the heavier it'll feel. Does any of that help? I feel like going from one strange example to another. Does any of that make sense, Ada?
Well, I'm a little bit confused because I don't know. I was kind of referring to like net force.
Yeah.
I don't know. Would it be the same thing?
Okay, so net force. Net force will tell you if it's going up or down. If the net force is up, then the thing's going to move up. If the net force is down, then the thing is going to move down.
But so for the bucket question,
Okay.
it was moving 2.2 up, but there was also the 9.8 moving it down.
Okay, so let's stop for 1 second. When it says accelerating from rest at 2.2 meters per second, so it's going up. That is the net acceleration.
Oh.
So that takes into account that like gravity, like it's going, it has to like the acceleration by the force done by the force going up, the F equals ma, this part for just the rope or bucket or whoever's pulling on this thing, it's got to be 9.8 plus whatever we see happening, which is 2.2, because it has to counter this. If you're not going at least this, then it's going to go down.
So then it asks for the net force acting on the bucket and the work done by the force, and the net force acting on the bucket is the 9.8 subtract 2.2 or added. I don't know.
So which question? Which ABC what?
7D.
Calculate the net force acting on the bucket. Sorry, somebody say something?
No, that's okay.
Calculate the net force acting on the bucket and the work done by the net force. And sorry, so what were you saying about that? Like what was the answer off or something?
No, I don't know. I'm just confused, but I can try and find the video.
Well, and also, you know what I think might help you, Ada, is if you work it out and figure out kind of what happens if you subtract like 9.8 minus 9.8 plus, and then see what the resulting answer is and compare. That might help you to actually go through the work of it and then compare the answers you get and then see how much that makes sense. Do you know what I mean?
Yeah.
Okay, like I saw this I don't know if you guys have heard of this thing. There's this thing called TikTok, and I saw a video on the weekend about how much more you learn when you write. Like I said something in the beginning. I don't want to be a pain in the butt, but I know some people take notes on their tablets and blah blah blah. When you write, when you physically write and work things out and draw while you're working or whatever, you will remember it better. Like there's all kinds of studies that show it and stuff like that. So that's part of the reason why I want you to do this. It's one thing for me to explain it. It's another thing just to kind of read it somewhere. But if you actually write it out, here's one way. Here's when I add it. Here's when I subtract it. Here's when I ignore it. And then what those three values will tell you.
Okay.
I think that'll help. But like I'm here all afternoon. If you're going to work on this and you have a question, I'll answer for sure.
Okay. I think I just mixed up the 2.2 and thought it was net force, and thought it was just extra force and
Oh,
not the net force.
okay.
And so for the questions, I was calculating the net force with the 9.8,
Oh,
but that didn't even make sense. So
okay. Yeah.
it's all good.
Okay. Cool. Next question. If there are.
I have more questions. Does anybody else?
Anybody want to take a turn for Ada runs?
I have like a lot, so
Well, let's just take turns then. Kate, what's yours?
page 249, number I think 2 and 3. Let me find my notes. Yeah, page 249, number 2 and 3.
Okay, page 249, number 2 says athletes who compete in downhill skiing try to lose as little energy as possible. Skier starts from rest at the top of 65-meter hill. Okay, so height is 65. VI equals 0, which tells us there's no kinetic energy. That's essentially what that's saying. I'm assuming. I haven't read the whole question. 65 skis to the bottom as fast as possible. When she arrives at the bottom, she has a speed of 23 meters per second. VF equals 23. So find the efficiency of the skier. Okay, so to find the efficiency of the skier, we have to know what the energy is at the top, what the energy is at the bottom. So at the top, and then kind of goes down. Up here, it's mgh. Up here, it's 1/2 mv squared. So the mgh, does it say her mass?
Okay, now I got it.
Oh, you're good?
Yeah,
You're welcome.
I just didn't know where to start.
Yeah, it's tricky. It's tricky when it does that. Now also notice it doesn't give the mass, but when you do this, mgh equals 1/2 mv squared, those m's cancel. Oops.
Oh, okay.
So that's one of the little tricks in there too. So you don't need the mass. All
Oh,
right.
well, that actually helps me for a lot of my other questions.
Good.
Because I was asking, like, why don't you need the mass to complete this? I'm like, I don't know.
Oh no. Yeah, that's why. How are you feeling? Your voice sounds better.
Yeah, I'm feeling fine.
Good.
Not sure about tomorrow, but I'll talk to my parents.
Good. A golf club. So you still want me to do number 3, right? Kate?
Yeah.
Right. A golf club with 65 joules of kinetic energy. So EK equals 65, which is 1/2 mv squared. Strikes a stationary golf ball with a mass of 46, m equals 46. The energy transfer is only 20% efficient. So I don't know how to write it. Efficiency equals 20%. Calculate the initial speed of the golf ball. Okay, so efficiency is energy coming out divided by energy put in, I don't know why I lowercase that I, times 100%. So we're going to put some numbers in. So efficiency is 20%. Now the energy going in is 65, right? Because golf club, yeah. So it's 65. the energy out is 1/2 times the mass, which is 46, times the velocity, which we don't know, and that's what we have to solve for. And then you're just solving for the unknown. Well, here we have this also times 100%. So if we divide both sides by 100%, this will be 0.2 equals half of 46 is 23, v squared over 65.
Can we just put 0.2 in right away on one side?
I was going to, but yeah, you can, as long as you're not doing this on the other side. Yeah, you totally can. Because it's all it's doing is changing the number you have to a percentage. It's a,
Yeah.
people are more happy with that, but yeah, totally. So 65 times 0.2, so that's 130, that's 13 over 23. I don't know what that is, or the root of that. 65 times 0.2 equals 13. Divided by 23 equals, of course, 0.5652, blah, blah, bleep, bloop. The root, 75%, or 75 meters per second. So V equals 75 meters per second. Does that ask for the speed? Yes. So then we don't even need a directione or anything.
I got a different answer, actually.
Oh, how does it feel to be wrong? Let me check. 65 times 0.2. It very easily could be me. That's why I said it so arrogantly. Divided by 23 equals this, and the root. What did you get?
I got 23.7 meters per second.
What's the right answer?
I'll check. I thought mine was right, but maybe not.
What am I doing wrong if you're right?
So the energy out is then,
Yeah, I'm right.
You're right?
I'm right.
What did you?
the
Oh,
shock.
46. It's not
Yeah.
46 kilograms, right? What is it?
Yeah.
26 grams.
It's 0.046.
Gross, Lyle. I should have.
Units.
Goodness gracious. Heavens to Murgatroyd. Did I mess that one? 0.0. Okay, what did I say? Ask you, how does it feel to be wrong? 65.
Mhm.
0.2 equals this, divided by 0.023 equals this. We get the root of that. Oh, I got 24 actually. It's 23.
Yeah. I got 23.7, but the answer is 24. So just
I got 24. So I guess I was most right.
maybe.
That's just because I rounded it. Kate, what was you were gonna ask something?
So the energy out is also kinetic energy, because
Doesn't have to be. Doesn't have to be. That's
so
that's same as what's going on up here. We could figure out the efficiency of this original question.
just using whatever we're given.
Yep.
Okay.
Yep. As
And
long as
since we
it's joules, right? Like it's joules over joules.
Yeah, and so since we needed to find velocity, we just used the one with velocity.
Yeah.
Okay.
Yeah. Who's got next? Mr. Truderung, you got a question? Or is that before we go on? Are you okay with that, Kate?
Yeah, that's good.
Just make sure, don't make silly mistakes with your masses. So that's embarrassing, especially when you record it and then openly mock another student. I'm gonna get fired before I quit. All right, Nathan, do you have any other questions?
Just one, page 241, number 3.
Better be just one, because this is the last one I'm answering today. Okay, which one? Number 3?
Yeah, number 3 on page 241.
I love questions like this. All right, page 241. So many roller coasters have loops where carts roll on a track that curves sharply up into the air. At the top, people are upside down. Oh, little personality from the textbook, and usually screaming. For safety reasons, many of these roller coasters must have a minimum speed at the top of the loop. In the roller coaster shown in figure 6, yeah, that's where it is. The cart must have a minimum speed of 10 at the top of the loop to make it around safely, excuse me. Assuming that the roller coaster starts from rest at the top of the first hill and there's no friction whatsoever, so it's completely efficient. What is the minimum height of the first Gel. So I'm just going to draw it. So it goes like this. This here is 16. This one, we don't know. So this here is total mechanical energy is 1/2 mv squared plus mgh. So we have the speed because we're told that it's 10. And we have the height of the thing because we're told that it's 16. So we add those together, and that's going to be the total up here, purely mgh. Is this, it says at rest probably? Roller coaster, minimum speed of 10 at the top of the loop. So it starts from rest, yeah. So whatever this number equals, it has to equal this up here. And then from that, you can solve for h. Does that make sense?
Yeah, that's what I got. Like I put mgh plus mv squared divided by 2 is equal to mgh plus mv squared divided by 2. But since the velocity up at the top is 0,
Yeah.
then that just got canceled.
Yeah.
And I guess the masses would just cancel because it's in each of the terms.
Yeah, so you can do like mg, I'll do h for the, I'll do a t for the h equals, well, I'll do the whole thing the way you said. So mgh t for the top plus 1/2 mv t for the top squared equals 1/2 mv squared, and the v here will L for the loop plus mgh for the loop. You can factor out an m from every one of these, right? So
Yeah.
if I rewrite this, GHT plus 1/2 VT squared equals, take an m out, 1/2 VL squared plus GHL, and then the m's cancel.
Okay. Yeah, that makes sense.
Yeah, and then this one will be 0, and then so on and so forth. Do you want me to keep going, or is that good?
That's good.
Anybody
Thank you.
else? Yep, no worries. Anybody else want me to keep going?
I honestly have no idea how you got there.
Okay, so let me start over.
Wait, could you just
Mm.
pause for 1 minute? I'm just trying to find my sheet so I can follow along.
Yep, just tell me when to go. Me, or is it hungry in here?
You might as well just start. I think I lost it.
Okay. So we're told that there's a starting place for a roller coaster cart, and when it's up here, it's not moving. We have no idea how high it is. We do know that when it comes down, no friction, so it's 100% efficient, which is a lie, but whatever. 100% efficient, it goes, spins around. When it gets to this part, upside down, we know here that it is moving at 10 meters per second, right here. And we also know that it's 16 meters high. So because of that, we have everything we need right here to figure out how much energy is in the system. Like a part A of this question could have said, how much energy is in the system? And then part B, how high is the starting point or whatever. Because what you do here, this 1/2 mv squared plus mgh, that will tell you how much energy is in the system. And because energy is not created or destroyed, the energy here has to be the same as the energy here. Now, in the real world, you're going to lose from friction and from sound and maybe from light if there's some sparks or whatever. But just for kind of our purposes, assuming nothing is wasted, which would mean that this thing would be silent, like silent. Do you imagine? Anyway, so Kate, are we okay to start there?
Yeah.
I don't know if I believe that. Yeah. Are you good or no?
So whatever we use to solve for the loop will be used to solve for the top part?
100%. All
Okay.
all the energy that is in that car right there will equal all the energy that is in the car right here. It just so happens
Okay.
here it's all potential. Here it's a little bit potential and a little bit motion. Could also ask you, how fast is it here, like at ground level? This is all mgh. This is all 1/2 mv squared.
Mm-hmm.
And so then this is a combination.
Okay. I
Like
think
to make it much
that
more
that makes sense.
make it much more simple, if there's a diving board, somebody jumps off, at the top, it's all potential. Bottom, it's all kinetic. I could ask, how high are they right here if there's X amount of joules, if they have that much energy right here? And then you got to figure out, because then it's a combination.
Because they're not on the ground, so there's potential and they're moving.
100%.
That's why.
100%.
Okay.
Okay, do you want me to keep going with this?
Yeah.
Okay, so GH here, we don't know the height. That's what we're solving for. So it's 9.8 times H. That's 0, so that's easy. Equals 1/2 v squared. So the speed here is 10. 10 squared is 100. Half of 100 is 50. Plus, and then it's 9.8. And the height there is 16. Oops. 9.8 times 16, 156.8. So that's 50 plus 156.8 equals 9.8 H. So this is going to be 206.8. I'm going to divide both sides by 9.8. Just solving for H. Did you get all that?
Yeah.
Does it make sense?
Yeah. So like what other questions would we deal with that? Just like
Roller coasters, slides, if you get a slide that's going kind of like this, or even like a diving board, like halfway down, if there's this a 10-meter diving board and they cannonball, it doesn't matter how they dive, they go down right here. You could be told that right before the water, they are going, I don't know, 24 meters per second. And then you have to figure out, if they're going 24 meters per second, then how much energy did they have at the very top, which would tell you how high that diving board was. Or I could give you all the information right here. 5 meters up, they're at this speed. How high is the diving board? How fast are they going right before they finish? Stuff like that. It would
okay.
have to be kind of like a height and falling kind of a thing to mix these things.
Yeah.
Does that make sense?
I think so.
Here's another one, just because I'm thinking what possible answers. Let's say you're in one of those skateboarding things, and if I kick a ball, because I can't skateboard, so I would just stand here and kick a ball. And if I kick the ball and it goes up 30 meters in the air, how fast was it the moment I hoofed it? Things like that. It's just kind of comparing the base level to height and then with speed.
So for the height, you would use the potential, and for the bottom one,
1/2 mv squared.
for which one?
V is speed.
Yeah.
Yeah, mgh is the height. Yeah.
Sorry, I was trying to find my sheet. I found it. I didn't do it. But what, can you just like put the camera on the equation that you used?
There, it's got everything but the with the answer.
So what you're saying is
Okay.
the first equals the second?
Every part along the path equals every other part along the path. Right up here, the energy here equals the energy here, equals energy here, 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 here. It just
Because it's not the same amount of work.
same amount of energy, yeah. And the it's just the height and the speed that change.
So you can use that to cancel and put your values in to find the other one.
100%. Yep.
Okay.
Cool.
Yep.
You good with this?
Yep.
Kate, you're good with this?
Yep.
What is next? Ada, you might be up. I don't remember.
Sure. Okay, when there is no displacement in either direction, there's no mechanical work done, right?
Correct.
There has to be displacement. So even if someone's like pushing on something a bunch, but it doesn't move, there's no.
There has to be displacement in the direction of force. If I push, if you trying to think of a situation. If I'm pushing on a car, that's a dumb example. What?
I get what you're saying.
Okay, good. Well, because I'm just going to be honest with you. I don't want to give away the question I have on the test. So let me read you something from the textbook.
In this one, it was like an employee pushing on a box and it didn't move.
Yeah, that's.
And after there was any mechanical work done.
But there can be motion, and there can be displacement without any work done. So here, if you are your force, you're this person, your force moves you forward. You're doing work on the bag this way, but not up or down, even though it moves. Does that make sense?
Yeah, so the vertical work was 0.
Yeah, exactly. Okay, good. Just making sure. Next question, Kate.
Page what? Sorry, don't know what page that is.
I don't either. Need some snacks at my desk. I'm running out. Some cookies or something.
Page 254.
250.
Number 2 and 3 again.
2 and 3. All right. Okay. Page 254, number 2. 65 kilogram student, mass equals 65. Holy moly, cat hair follows me everywhere. I'm at work. Get out of here. Mass equals 65. Student climbs 5 meters. Displacement is 5. In gym class at a constant speed of 1.4. V equals 1.4. Determine the time it takes a student to climb up the rope and then the power. Okay, so for part A, we want T and we want P. Okay, so the time, they're going 1.4 meters per second for 5 meters. So speed is distance over time. If you got 1 point.
Oh my goodness.
What's that?
I just did not even think about that.
Oh, that's okay. So 5 divided by 1.4. 5 divided by 1.4 is 3.57. So time equals 3.57 seconds to get all the way up. Power equals, what is it? Energy over time? Is that right? That's the easy formula. Yeah, okay. The energy in this case is going to be 1/2 mv squared because it's kinetic over time. So that's 0.5 times 65 times, they're going at 1.4 squared all over 3.57. 1.4, oops, whatever, 1.96 times 65 equals that, divided by 2 equals that, divided by 3.57. 17.8, so 18 watts. I had to think for a second.
Okay.
Does that make sense?
Yeah. I just totally forgot to go back to the basic triangle
Yeah.
formulas.
For sure, which totally makes sense. Good with that?
Yeah.
All right, number 2, or number 3, that was number 2. A student uses a pulley to lift a mass in the air. Assume the mass is lifted at a constant speed. Describe one way you could determine the power of the student when she is lifting the mass. What? Assume the mass lifted at a constant speed. Describe one way you could determine the power. Okay, so, well, power is E over T. E equals 1/2 mv squared and mgh. So I would do it this way. Describe a way you can determine the power of the student. She's lifting the mass, constant speed. If you know what the speed is, you know, and you can time it, well, you would need to time it. Yeah, that's a strangely wide open question. You'd figure out, you'd use one of these two things divided by time. You know, based on the height, how far it goes, obviously you would need the mass. And if it's telling you a constant speed, but it's not telling you what that speed is, well, then you'd have to do it this way, mgh over time.
Mm-hmm.
Although really, if you knew the height and you were timing it, then you'd be able to figure out the speed. So it's a bit weird. Does that make sense?
Yeah.
When I ask you a question like, you know, explanation or definition, it's not weird like this. It's a little,
That's the part I'm most worried about.
Yeah,
Is
like-
explaining things.
it'll be more like, you know, how does one get negative work? How does one get zero work? You know, even though there's force applied and stuff like that. It's more kind of definitive versus
How-
hypothetical.
How
What
does
kind of
zero work
definition?
happen?
Zero work happens if there's either zero force or zero displacement. Push as hard as I want
Oh,
on this wall next to me, and you might say, "Oh, that guy's working hard." Well, technically, nerdily, no, because there's no motion.
I see.
Lots of force. Yeah. Did you say something, Ada?
Yeah, what, like, can you like give like the range of like what sort of, like, we're gonna be asked about definitions
A little bit.
and explaining things,
A little bit.
but it's all like the stuff that you posted on the classroom, right?
Oh yeah. Stuff we've posted, stuff we've talked about. And for what it's worth, like if it says look at table 4, it doesn't mean memorize table 4, but have an idea what's on table 4, for example. You know what I mean?
Mm-hmm.
I also have no idea what the like transfers of energy mean. Like,
Like this.
yeah.
Okay.
Wait,
So
where is that?
this is a good example. This is page 244.
Okay.
This is a good example, like of a table. Like you don't have to memorize this, but you should have an idea of what's on it. You should have some idea of things that stick out. So if I were to tell you, or if I could literally ask you a question on the test and say, which is more efficient? Because honestly, it more depends on an understanding than memorizing. If I say to you, what is more efficient, an electric vehicle or a gas-powered vehicle? What do you think would be more efficient?
Gas powered.
You would think a gas power is more efficient?
I don't know.
Oh, that's interesting. Why would you think that? Good thing we're having this conversation. Why would you think?
Because that's what our cars are.
Okay,
Gas powered?
all right. Well, just so
I
you
mean,
know, electric is more efficient. Generally speaking, the world moves towards efficiency. So anything newer is almost always more efficient. And so electric vehicle is like newer
except the
technology.
bicycle.
What's that? Yeah, that's what I say generally. That's what I say generally. And that's also kind of fascinating, isn't it? 90% efficient. Like that is high efficiency. Do you remember when go ahead?
I thought electric powered vehicles were just more environmental than efficient.
But that's part of it, right? Because if there's wasted energy, it becomes like it's noise pollution, sound pollution. Well, those are the same thing. Like air pollution, all kinds of stuff. So if it's more efficient energetic wise, like if a gas car was 90 or 100% efficient, we wouldn't be complaining so much about the climate and things like that, because there wouldn't be almost anything coming out of the exhaust pipe. There wouldn't be any pollutants because we'd be able to use it all. Do you know what I mean?
Yeah.
I was going to say something else caught my attention. I mentioned in class heaters, very, very efficient, because a common waste energy is thermal. What is the waste in a heater? Light, because the heat is what you want. So it's going to give off a bit of a glow. So there's your waste energy, but it's 98% efficient. A loudspeaker is 1% efficient, which is crazy. 1%. The rest, the waste given off, is heat. Animal muscles at the bottom here. Muscles, 20%, and it's heat. You heat up, and then you sweat to try and cool down. So to go back to your original question, Kate, does this answer it at all? I don't know what it was. I just remember.
Yeah, I'm starting to get it. I mean, it's just thinking about where its energy is coming from and what it turns into,
Sure.
right?
Yeah.
Okay.
At its most basic, its potential to kinetic. It's stored up, and then it's being at its most basic. You can break it down into like chemical, like our potential energy as people is food, nutrients and stuff. That's our chemical potential energy. But I don't spend a whole lot of time breaking all those down, because let's focus on the ones we have a formula for. You have other questions about this? This is a good.
So like,
this isn't. You don't need to memorize this. Just get comfortable with it. Like remember a couple different things. Photosynthesis is only 5. Like the one that jumped out at you was the bike. Remember that 90%. It may show up useful on the test.
I'll take that as a warning.
Who's got next question? I don't remember. Oh, I think it's Ada has the next question, right?
I don't think I have any more questions yet.
Okay.
I decided that I wasn't gonna work yesterday and have a Sunday off, and it's coming back to bite me in the butt.
Well, rest is good for you too. There's pros and cons to every decision you make.
Mm-hmm.
It's gotta be whether or not it's worth it. What do you got next, Kate?
Okay, to the test review.
Okay.
At the page, I don't even know what. I have screenshots of it, and I don't have the page numbers. Number 37.
Page 263, a roller coaster. I love these ones. You want me to do this?
I hate these ones. Yes.
Okay. Well, let's learn to love them. A roller coaster descends 55 meters from the top of the first high point to the first low point. Okay, so let's just say this. So this here is 55 meters. The roller coaster converts gravitational potential energy to kinetic energy with an efficiency of 50%. So what you could say is 0.5 mgh equals 1/2 mv squared. Are we okay with that? Because only 50% of the potential gets converted.
Oh. Okay.
So it's like whatever you have here, divide it by 2, cut it in half or whatever, and then it'll equal that.
Yeah, I would probably do that last, but yeah, that makes sense. Just
And
put
yeah,
it all
you
into
totally
a
can.
formula.
You totally could do it last, unless it's asking for speed and stuff, then it could be a bit tricky, but
I think it is.
what is the velocity of the roll call? Yeah, at the bottom of the first low point. Okay, so do you want me to do this one?
Yeah.
So mgh, so again, the m's can cancel. They're on both sides. We can just cancel that. 0.5 times gravity is 9.8 times 55 is the height difference. Everything's relative. Notice also we have a half on either side. We can just cancel these just to save us some time. That's v squared. So 9.8 times 55, you get the root of that and you have your speed.
Well, that was a lot easier.
$23 is what I got.
I think that's right.
But when you said, for what it's worth, like you said, oh, I'll probably do the 50% later. So let's just say mgh equals 1/2 mv squared. M on both sides, get out of here, get out of here. So gh, 9.8 times 55. Well, another way you could set this up, like I did it this way. So this equals v squared. But let's say, so at this point, you'd still have to, do that 50%. But if you set it up as the efficiency equation, efficiency equals like E out over E in. Well, if the efficiency is 0.5, that equals, this is this is 1/2 mv squared, and this is mgh. M's cancel. It's just another way of kind of looking at it. You have your G, you have your H, you multiply it by this, divide by 1/2, take the square root. It'll give you the same answer. It's just
Yeah, they just cancel out.
Yeah. Yeah.
Okay.
That help?
Yep.
It's your show, sister. So whenever you're ready to ask the next question, fire away. Ada, jump in.
38B.
A CFL is 17% efficient. How much energy input would be required? Okay, and what type of energy is the waste output, and how much would be created? Okay. Which part? Both parts of B?
Yeah.
Can you tell me the answer to A? Do you have that in front of you by any chance?
Yeah. 1400, I think. Let me
Okay.
check.
Do you have the unrounded version?
1480.
Beautiful. Thank you. Okay, so 1480 is what we're starting with. That's the energy to be required. So what type of energy is the waste output, and how much would be created? Okay, so how much would be created if it's 17% efficient, then 83% of this is waste, right?
Okay.
Does that make sense or no?
I guess it does. I just never thought about it.
Okay, so, or you could figure out 17% of this, so 1480 times 17%, 0.17, and then just find the difference. It's two different ways of doing the same thing, times 0.17. This one's just a touch longer, 251.6. So there is 251.6 joules of useful energy. 1480 minus 251.6, which would be the same thing as multiplying by, the 83%. 251.6 minus 1228.4. So 1228.4 joules is waste.
And would that type of waste be heat or thermal?
Yeah. If you said heat waste, I'm okay with that, but yeah.
Okay.
Yeah. Like when it doesn't say especially if this is a test on here, you could go back to that table, that table that we were just showing and say,
Yeah.
let me see, what is the, oh, it doesn't even have the light on there. Yeah, so it's a little bit of kind of an expectation. When in doubt, it's
Go to
thermal.
thermal.
Yeah, it really is.
Well, I mean, also just thinking about a light bulb, it gets hot. So
Yeah, totally. But the only place where thermal, almost, the only place where thermal isn't waste is if you're talking about an electric heat. Yeah, because none of that is, that's all desired.
Okay.
Yeah.
Number 48.
A weightlifter. Okay. This is what Mr. Clausen. A weightlifter lifts 150 kilograms weight with 1910 newtons of force overhead to a height of 2.8 meters.
I think I might go
You're allowed.
because I need to work on the review. But if I have questions, can I just email?
You bet.
Okay, thank you so much.
Yeah, you bet. See you later.
Bye, guys.
Okay, so it's page 264, numero 48. A weightlifter lifts 150 on force to overhead weight. The weight then falls back to the ground. Determine the net force acting on the weight for both the lift and the drop, and create, okay, the force displacement graph, don't worry about it. Not gonna be on the test. If you'll notice, we didn't spend any time on it in class, really.
Okay.
So, oh, is that your whole question?
No.
Okay.
I mean, I think I could probably figure this out, but I don't know.
Well, let's have a look. So the going down is the easier part. The net force acting on the weight for the drop. So let's just do that first. That's the easiest. So F equals MA. The mass of the weight is 155. 155. Acceleration due to gravity is 9.8. 1519. So 1500 newtons. So that's going down.
Yeah.
And that's basically, that's done by gravity. Going up, it's a bit trickier. It tells us that the weightlifter uses 1910 newtons of force. So F equals MA. The force that the weightlifter is 1910. That mass is, wait. Oh yeah, the force, okay. 1910, and so the mass is 155 times the acceleration. So (1910) divided by 155 is 12.32, we'll say. So acceleration equals 12.32. No, this is, we were talking about acceleration. I want to make sure I don't make a mistake here. Lifts that weight with 1910 newtons of force overhead. So that's, okay, but we want the net force acting on the weight. Now I'm doubting myself here, because so this person is acting against gravity. So I want to add 9.8 to this. But it's telling you, see, I don't like questions like this because it's telling you they're using 1910 newtons of force. And if they're telling you that, then really, if this is the force of gravity, then really it should be a difference. It should be the net force going down would be going up would be 400 newtons, because this is always there. You know what I mean? Like gravity is always there. And when you're told when you're told that the weightlifter is using 1910 newtons of force, the net is actually 400. I'm just going to double check the answer myself. I don't like the way this one's worded. 264. What is this? What number? 48?
Yeah. Well, we got one part right.
Yeah, it's saying
Did we? No, we did not. Yes, we
300.
did.
But why would it be 300? This is what he used going up. Gravity used that going down. The other way, hang on one sec. Give me one sec. Yeah, no, the other way I would do it would be way more. I'm gonna have to look this one up. For what it's worth, you're not gonna get a question like this.
Yeah.
You're trying to tease them apart like this. This bothers me. Why is it this? You know, give me 1 second. Let me look at something here. Oops. Yeah, I don't know. I think the best thing I can do for you in this moment is to say, let it go. See, this is one of those things. This is one where, like I tell you, I don't like the wording in the textbook, and I'll always make sure it's clearer.
Yeah. And it's, I mean, I think, I don't know.
You think what?
I don't know. It's like, it sort of makes sense about how to do it, but at the same time, it's like, what?
Yeah, see, but that's what I don't like about when it's gray area like this, because then you start thinking, well, okay, well, this makes sense, that makes sense. Like one way, you could say, like, if we find the difference in the acceleration, so 12, whatever, 0.32 minus 9.8, 12.32 minus 9.8 is 2.52. And then, so 155 times 2.52. Yeah, see, it's still 400. Yeah, I don't know. That honestly, it might be a typo.
Okay.
It might be a typo. So I don't know how else you would do that. Sorry, I hate leaving stuff like that, but I think it's best not to dwell on it. Other questions?
Yeah. 53.
Man is pushing 11 kilogram lawnmower against a frictional force of 86 newtons, 22 meters. What is the minimal force that the man needs to push with in order to keep the lawnmower going? Okay, well, if the friction is 86, then, you know, one could argue 86.0001, etc.
Yeah.
You know, but I would just say 87, keep with sig figs and everything like that.
Mm-hmm.
So he would need to push with 87 to overcome that frictional force, because if he's pushing with 86, then nobody's going anywhere. Know what I mean?
Mm-hmm.
So that would be, this is 53A. So yeah, I would say 87 newtons. Push with in order to keep the lawnmower moving. Calculate the amount of energy. You want me to do all of it? A, B, and C?
Yeah.
B says calculate the minimum amount of energy required for the man to push the lawnmower the required distance. Okay, so energy is work, which is force times displacement. His force is 87, and the displacement is what, 11? Saw some other TikTok video where some trick about how to multiply with 11. I gravitate toward these nerdy things. 957 equals 957, which would be 960, I'm guessing. Yeah, 960 joules. And if the man uses 2180 joules of energy to push them over at a constant speed, what is his efficiency? Okay. So this, again, not the best worded question, because I guess it's assuming compared to this. Let me just check. Are these the answers it's giving? I would assume. I just want to make sure before I move forward. 265.
Yeah.
Number 53.
Oh no.
Oh, it says 86. That's irritating.
Bees.
Oh, B is 1900. What? Oh, B is calculate the minimum amount of energy required for the man. So if he was pushing for the man, yeah. Why is the answer so much bigger? What did it say, 1900?
Yeah.
What in the world? So 1900 divided by 11, it would say he would need that much force.
Oh my.
Why? Hang on. Yeah. What is going on?
I just keep picking the worst questions.
Yeah, like, because that doesn't even make sense. Like, as objective as possible, how in the world does that make sense? Because what I was going to say is if we were talking net force, like if it says that there's 86 newtons of friction, if he applies 87, then the net force is 1 Newton. So the net force would be 1 times 11. This is garbage. Oh man, ignore it. I don't know what to tell you. Sorry, this is terrible. Day before the test that you're getting stuff like this. It makes no sense. What other questions did you have?
Well, we can do C.
If a man uses of energy to push them more at a constant speed, but we would need something to compare it to. Like it's, well, I guess, yeah, we can compare it to the 1900.
Yeah, we may as well.
So it's just 1900 divided by 2180 times 100. And if that's not the
Oh
right,
yeah,
right?
that's right.
Yeah.
Okay, then just forget that. 57.
Okay. Time for a good one. An incandescent bulb is only 5% efficient. How much waste thermal energy is produced by a 100-watt bulb in 1 hour? Okay, so a 100-watt bulb, so these energy ratings, these would use, for energy ratings, would use kilowatt hours. This is one of those times that we would use a kilowatt hour. So it would be
0.1.
and so and only 5% of that. How much is waste? Would be 95% of 0.1. And then it would be in kilowatts. We could do it in watts as well, just to get a different answer. Which way do you want to do it? Well, I'll just walk you through it. Okay, so 5% efficiency. Efficiency equals the energy you're getting out over the energy you're putting in. How much waste thermal energy? Okay, yeah, in 1 hour. If it's 1 hour, then it's 0.1. So it's 0.05% efficient equals the energy you're putting in is 0.1. So the energy that you're getting out would be 0.005 kilowatt hours. That's what you're getting out, which means if we change this to 95, because that's what's kind of staying in, if you will, or just this, subtract this to find the difference. So it'd be 0.995 as waste. It's the hour that makes you go to the
Okay, so
because of the rating.
the textbook converted it to joules.
Oh, of course it did. So I will do that.
Guess
for
you can't have a decimal.
All right, give me 1 sec. Sorry, getting a text here. All right, so if it's talking about joules, then the hour, it's 100 watts per hour, then it's just, so it's 95%, right? So the waste would be 95 joules in an hour as waste. See, and that's what I want to put in an hour. But as soon as you put 95 joules per hour, you've got a different kind of measure. But does that make sense? If it's supposed to use 100 watts in an hour and it's only 5% efficient, well then 95% of 100 is just 95 joules.
Wait, what?
It's 95% efficient.
Oh yeah, because I see.
Yeah.
Okay, there was a question on one of the assignments that was like, show that 1 kilowatt hour is something. Yeah, that 1 kilowatt hour is 3.6 megajoules.
Yeah, I think that was the lesson that I forgot to record. You don't have to worry about that. Like that's not anything you're going to encounter. It's more of it's almost like every once in a while you're going to get something where they say convert D equals AT plus 1/2. I'm making stuff up here. AT squared. This is VT. Convert this to D equals VI plus VF over 2 times T or something like that. It's like, it's that kind of question. Don't worry about it. That's like a calculus proof. So don't worry about it.
Okay.
Okay.
Yeah. I think I had one more. Let me just find it. 59. Some of the ones like with the costs I don't always get right, so
Microwave operates at 127 watts. So if we're doing kilowatts, 1.275. Okay, so this is page 265, number 59. Energy is 1.275 kilowatts. Electricity is 5%. So the cost is 0.05 per kilowatt. That's a per kilowatt hour. It's gonna give me time. What is the cost of heating a cup of soup in a microwave for 2 minutes? Okay, so this is, you can multiply this, and then times the fraction of the hour. So 0.05 for every hour. Oops, 275. But this isn't an hour, it's 2 minutes, that's 2 over 60 or 1 over 30. Does that make sense how I did that? Why I did that?
yeah.
Okay. So 0.05 times 1.275 times 2 equals that, divided by 60 equals 0.21 cents. So it's not 0.21 of a dollar, it's 0.21 cents because of all the what am I looking for? Decimal places. What are you laughing?
That's cheap.
Yeah. Oh, yeah. And as it should be, right? Like if you put
Yeah.
it, and it should make sense like that. Like if you're putting a cup of coffee in a microwave, like it should be like nothing kind of a thing. Does that make sense?
Yeah. And then what is B?
B says, describe 2 possible hidden costs of heating the cup of soup. Hidden costs? It might be like, the fact that the microwave is always on, so it's going to be using energy. very, 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 very little, right?
Yeah.
Because it's got the time display and stuff, so it's almost negligible. And then also maybe, you know, the amount of time that the light is on when you open and shut the door, you know, like that's because the amount of energy obviously is very, very tiny. So I guess if we're comparing, then yeah, like the light's going to be on for a few seconds, you know, the microwave is always on, kind of a thing, stuff like that.
Yeah.
That's
Okay.
a silly question, but yeah, that's kind of how it would break down.
And then things like number 58.
Describe and take place in nuclear power plant when it's generating. Yeah, that's too much without having kind of a table in front of you. Like that's having to memorize kind of facts, and I'm not a proponent of memorizing facts.
Okay. Because
That
I sort of skipped most of those questions and just
Good.
did the work ones.
Good. Yep. Like you could say, and when it says describe the energy transformations that take place. So I don't have the, you know, how I don't remember exactly how a nuclear, I say exactly, I never knew how a nuclear power plant worked. But the energy transformation, I know it has to do with heating up water. Like the atoms, when they're split, they heat up water. The water converts to steam. Steam turns a turbine, and then that creates energy. A simpler version would be kind of radioactive energy into thermal energy. You know what I mean? Like stuff like that. But you wouldn't be
Mhm.
asked like the specifics of that stuff.
Okay.
Whatever's like kind of in the notes, and if it refers to something like a table, you should be aware of the table. Don't have to memorize it. But if it's in the notes, then yeah, you need to know it.
Okay. And then number 63.
63, 610 kilogram racehorse able to accelerate from rest to a speed of 14 meters per second in only 1.1 seconds. Assuming acceleration of the racehorse is constant, what is the distance required by the horse to reach this speed? To reach what speed? Oh, it's just, oh, so this is the distance question. So that's a kinematics question for part A.
Right.
Like you have, this is 63, page 266. So BI equals 0, BF equals 14, acceleration equals 1.1, and then so you'd solve for D. Do you want me to do that?
Yeah, sure.
So we're going to use a formula that doesn't have or require time, which is BF squared equals BI squared plus 2AD.
We have time, don't we?
Oh. What is 1.1? Oh, that's time. Sorry. Yeah, you're right. Thank you. That's time. That's not the acceleration. Let's go back to the drawing board here. Thank you. D equals VF plus VI over 2 times time. Read that wrong. So D equals VF plus I is 14. 14 over 2 is 7 times 1.1. So the displacement, the distance it would need is 7.7 meters.
Okay.
Good with that?
Yeah.
Part B, what is the minimum amount of energy required by the horse to reach this speed? Well, that's 1/2 mv squared. The horse is 610 kilograms, so 1/2 times 610 times, and what was the speed? 14. Lots. 60,000 joules. It's 2 sig figs. Gonna have to be this way: 6 times 10 to the 1, 2, 3, 4, 10 to the 4 joules, or 60 kilojoules. Does that make sense how I did that?
Yeah.
Last, how much power does the horse have during the acceleration? Well, now it's this, well, or the non-rounded version divided by the 1.1 seconds.
Mm-hmm.
54,000 watts. It's a lot of power. 1 second. 5, 4, 3, 4, 5, 4, 5, 4, 5.
Okay.
Yeah. Does that make sense? Helpful?
Yeah, I'm just looking at 64.
Okay. Oh, I have that one
Is-
crossed out in my textbook. Cyclist competing in a race decides to pass the fellow cyclist. The initial speed of the cyclist is this, and he has this of power. Bicycle is able to convert 90% of the. There's so much involved in there. That's probably why I have
That is
more crossed
a
out.
lot of information.
Yeah, it's actually crossed out in this textbook. So
Okay.
yeah,
It sort of freaked me out for a moment.
yeah, that's lots. And in all honesty, I feel like I'm going to do this after I'm done with you because I'm just curious. I just want because I like math. Anything else, sister?
Now I'm just looking back at the ones I skipped.
Sure.
Like number 12.
From the from the review.
Yeah.
2,000 kilogram rock rolls down a hillside 40 meters per second and crashes into a large tree where it comes to rest. The tree does not move. How much work was done on the tree by the rock? 0. Because the tree didn't move.
Okay, that's what I thought.
Yeah. See, it throws in these numbers in there, right? Like, oh, okay, so it's MGA,
Yeah.
1/2 mv squared. The tree doesn't move, done. Anything times 0 is 0.
So just for sake of writing it out, how would that look? Like,
I honestly, like, if you could write it just in a sentence, but you could also say, this is a work question, right? Work, how much work? Okay, so work equals F times D. D equals 0. Work equals F times 0. Like, this is if you want to write it all out. Work equals 0.
okay, yeah.
Yeah, like there's just nowhere to go with it. And even then, it doesn't really tell you what the force, like you would have to do some figuring to figure out the force of that. You can get the energy of it, but the force is different. I don't know off
Yeah.
the top of my head how to calculate the force. 2,000 kilogram rock rolls down a hillside at 40 meters per second. So you'd have to kind of figure out the acceleration. Yeah, I don't know how to do it off the top of my head. So that's part of it, you know, like it's just there's no displacement, so there's no work.
And so the work is just like the displacement is 0 because
Tree didn't move.
yeah, okay.
Yeah. It's like how much work was done on the tree by the rock. If you were asking how much work was done on the rock by gravity, well, there's a different question.
Mm-hmm.
And even then, I don't think there's enough information to help us solve it.
So it's like the work is of the thing that it hits, sort of.
Yeah.
Okay.
Work is force times displacement. If either one of them is 0,
It's 0.
yeah. And if work is 0, at least the force or the displacement is 0. Like you could get, this might trick some people if you're told, so-and-so threw a tomato at the wall, not at the wall, at a plant. Oh, I'm terrible when it come off the top of my head. At a target with a force of 6,000 joules, but the work done on the target was 0. Why? Because the target didn't move. Kind of a thing.
Yeah. Also, what kind of questions are we gonna are we gonna get any about renewable versus non-renewable energy?
Don't think
Like
so.
I don't.
Let me just check. Nope.
Okay. Because I don't know how to.
No, you're good. Don't even think about it.
Okay. I think that I am ready now.
Cool beans. If you get a question between now and then, feel free to email me.
Okay, thank you.
Yeah, you're welcome. Kate, are you still there?
Yeah.
This was like a fair amount of time, just me and you. It's all been recording. Are you okay with this being posted in case people have questions of these types?
Yeah, that's fine.
Okay, just making sure. Thanks, kiddo.
Mm.